start recording whenever. Okay. All right. Hello everyone. So today is gonna be the sixth, and I believe the final session of our mind-inset number theory tutorials. So today, what I thought we were gonna be doing is just some Diophantine equations. Okay, so I guess Diophantine equations is kind of like a big word. Um, it's actually a pretty simple concept, so I'll explain that first. And then what I'll do is I'll go over some techniques to solving these Diophantine equations, and then we'll finish off with some example problems, okay? So essentially what a Diophantine equation is just any equation that have solutions in integers, right? So I'll write that down. So it's any equation that any equations that have solution in integers. Okay. So if we think about something like sure, like x squared minus 1 is equal to 0, that's a pretty standard expression, right? And we can see that it has solutions +1 and -1. So that could be classified as a Diophantine equation. And since we're doing number theory, we're restricting ourselves to only just the integers. If we're doing something more like algebra, we might be looking at something like reals or complex numbers, but in number theory, um we don't really concern ourselves with that, right? Okay. So I mean, if it's just one variable, then you can kind of solve it really easily, right? But then the real fun kind of starts when we have more than one variable, right? So say we have two, we have x and y. So an example problem, let's just start right now, is we can think about x squared. So that's kind of like our first problem. So x squared is equal to y squared plus 7. And we want to find all pairs of solutions x and y in the integers, right? So here the integers can be positive or it can be negative. That is okay. Um, so that actually kind of leads me to our first trick, kind of like the first trick to solving these Diophantine equations, and that is to factorize them. We want to factorize them as much as we can. So here we can just do some manipulation to get x squared minus y squared. Why is my whiteboard not working? X squared minus y squared is equal to 7. We can factor that by x plus y. No, x minus y, x plus y is equal to 7. Is equal to 7. Okay. Um, so here's where the integer part actually comes in, right? Because on the left right now we have a product of two numbers, like x minus y is just a number, x plus y is also just another number. And on the right we have a constant, right? We have a constant, so that's 7. So we can actually kind of just go by casework. We can kind of just like analyze what the factors of 7 are, because we know that x minus y and x plus y are actually just factors of 7. So if we can factorize it to something like this, then we can sort of just brute force our way through the rest of the problem, right? So in this case, we have these cases, right? So what are the factors of 7? Well, that's just 1 and 7. So we can have x minus y is equal to 1, x plus y is equal to 7. That's one of the cases we can have. Or if we're keeping it in the positives, x minus y, x, oops, x minus y can be 7, and x plus y can be 7. And all of these things, we can kind of just solve them with simultaneous equations, right? It's pretty straightforward, so I don't think there's any need to go into that. And then obviously we also have the negative cases, because guess what, they can be negatives as well, right? So we also have another solution set, which is x minus y is -1, and then x plus y is -7. So this will also work, and obviously this the other one, x minus y is -7, x plus y is -1. So I'll just write that. So that is our 4 different cases for the solution, and all we need to do is just to solve them simultaneously, and it will be all good, right? We would have found all the solutions. Okay, so that is one type of factoring where you can utilize sort of like the difference of squares, right? There are also some other types of factors. So another problem, let's look at this problem. If we want to find all integers, again, x, y, such that x times y is equal to x plus y plus 4. I'm just choosing 4 here because it makes the final thing a little nicer. So if we want to figure this out, all we can do is we can also factor this, right? Because what we can do is we can do xy minus x minus y is equal to 4. And then we can factor it into x minus 1, y minus 1 is equal to 5. Right, just adding 1 on both sides, and you can actually see it factorizes. And then from here, we can do the same thing where we kind of take the factors of 5, -1, -5, 1, 5, stuff like that. And then it should all be solutions to our x and y in this equation. So that's also pretty straightforward. So I don't think there's anything I need to do to go off. I don't think there's anything I need to do after this, right? And then there's also a third kind of scenario. If we have not only our x times y, what if we combine it, right? So here we had x squared and y squared. Here we have some kind of random terms. We have like x to the power of 1, y to the power of 1. What if we combine it? What if we do something like x squared plus y squared is equal to x plus y plus 2? Something like this, right? Then it might not be kind of immediately obvious what you need to do to factorize this. Because you see on the left, we got the sum of squares, and we know that's kind of not factorizable, right? So what we can do is we can kind of do this neat little trick because I know that um well I know something that is 2x minus 1 squared. That will give me 4x squared minus 4x plus 1. Here, right? So if I have this, well, then you kind of realize that, wait, the coefficients of these two, the x squared term and the x term is kind of the same. So that is pretty good, right? That should be pretty useful. So let's just think about that. Yeah, so actually what I'm going to do is in order to make the coefficients kind of the same, and I want it in this form, I'm going to multiply both sides by 4. So then we have 4x squared plus 4y squared will be equal to 4x plus 4y plus 8. All right, and then you see how we have this 4x, 4x squared, 4x, 4y squared, 4y. And that's pretty easy to factorize, right? That's not too bad to factorize. So what we can do, I'll move the 4x over to the side. You'll see why in a second. So I'll move the 4x over here. So I can get 4x squared minus 4x. I'm going to keep the 4y to the right for now. And here we can add 1 to both sides, and we can factor it into 2x minus 1. Like so. And here now you might be thinking, right? If I just move the 4y over straight away, well, then I have a sum of cubes again. So that's not very good, right? I have a sum of cubes again. What am I going to do? Because it's not in the product. So here's the interesting thing, right? So I can move the 4y over. but I can also think about it another way. So that's the interesting thing about squares, because if you square a negative number, it also gets you back to the positive number. So I can also do it like this. So if I have 2x minus 1 squared, that's just the previous part. I will add 1 minus 4y plus 4y squared is equal to 9. So if I do something like this, then I actually have 2x minus 1 plus 1 minus 2y whole squared is equal to 9, right? And that is pretty interesting because what did we say before? The x and y are real and they're integers. So if the x and y are real and they're integers and they're all squared, what does that mean? That means they're both greater than 0, right? They're both integers greater than 0 and they sum to 9. So then what we can do is we can just kind of do the casework, or we can just analyze, okay, what could be 2 squares that sum to 9? Off the top of my head, I actually can only think about the fact that 3 squared plus 0 squared is equal to 9. If you think about it in any other case, I don't believe there's any other solutions. So then that means either this one's got to be 0 and this one's 9, or it's the other way around, right? That's really the only two possibilities for this to actually make sense, because we got 2 positive squares and they sum up to 9. And yeah, basically what you can do is you can just analyze that, do your casework, and you'll end up just fine. Okay. So that's the 3 kind of cases for actually factorizing a Diophantine equation, right? Here, so remember how before I said we kind of can't factorize the sum of 2 squares? That is actually not exactly true. There's a special case where you can actually factorize the sum of 2 squares. So I just thought that would be a interesting kind of aside to show you guys. So if we look at, so if we just consider this expression, I have x to the 4 plus 4y to the 4. So we kind of see x to the 4 is some kind of square, right? It's x squared, and then plus 4y to the 4. Oh, I guess it's not really kind of the square, but okay. You can see why I thought it was a square. Actually, no, it was okay, this was a square. This was 2y squared whole squared. It's x4 plus 2y squared whole squared. Yeah. So it is the sum of 2 squares. Okay, so we're gonna try to factor this expression. And this expression actually has a name to it. Like some mathematician actually factorized this and then gave it a name. So I'll do the factorization first and I'll tell you. So what we can do is we can manipulate it by adding a few times. So I'll add this time. I'll do it like this. So I have x to the 4 plus 4y 4. I will plus 4x squared y squared minus 4x squared y squared. Right? I'll do it. I'll do something like this. And that is actually motivated from this identity all the way up at the top. So this one over here. Because you see how I have a 4 here, and I'm just trying to make another term in the middle that has the same coefficient of 4. So then what we can do is we have actually factorize this, because that is a perfect square, if you can recognize it. So that would just be 2y squared plus x squared all squared, right? You can expand it and we get the same thing. We still have this thing to minus. And the reason why this x4 plus 4y to the 4 is special is because this middle term that you add in is actually also a perfect square itself, right? So now we have a difference of squares. So that is really cool. So we can factorize it like this. 2xy all squared, right? So we'll get, by the difference of squares, this identity plus 2xy. Okay, and that is equal to x to the 4 plus 4y to the 4. So we kind of just factorized a sum of two squares, right? So this identity is actually called the Sophie Germain. The Sophie Germain identity. You don't actually need to know that. I just thought it would be a interesting aside to know, to kind of like, if you want to solve more Diophantine equations, if this does come up, then you can kind of boom instantly recognize, wait, this is factorizable. And then by that point you would have been like, okay, that's pretty cool. I think the problem is pretty much solved. Maybe, I don't know. Okay. So that's kind of all I wanted to talk about on factorizations to solve a Diophantine equation. And now what we'll do is we'll move on to some other techniques, right? And the first thing I'll talk about is using mod. So modulus, which is basically I'm analyzing the remainder when I divide it by something, right? This is actually really useful because of some or just because of some few facts, right? The first thing is if we just analyze the squares under a certain mod. So if we analyze mod 3, if we think about it in mod 3, and we consider x squared under mod 3, then we might already know that x squared can only be 0 or 1 under mod 3. And you can kind of do your casework like on your own, and you kind of just realize that this has to be true. Why? Because you either have 1 squared, you have minus 1 squared, or you have 0 squared. So they only really lead to 0 and 1. You can analyze squares in mod 4. And that will give you x squared is really congruent, really only congruent to 0 or 1 under mod 4. So that's the two big ones you can kind of think about when you do these kind of equations. There's also another one I want to point out, which is kind of less well known. So these two are obviously quite well known. If we analyze the cubes, so x cubed under mod 7, that actually gets pretty interesting, right? Because let's just do some examples, right? If we do, so obviously 1 cube we got 1, and we got 8, 27, 64, 125. I'll just go up to here. If we analyze them under mod 7, this one is 1. This one's 1 mod 7. This one's 6 mod 7. Well, that's just minus 1 mod 7. What is this one? This one, because 7 times 9 is 63, so this one's 1. And then this one, I believe it is, this one is minus 1 mod 7, I believe, because 126, 126 is a multiple of 7. So, I hope you can see that this is actually minus 1. But I hope you can see that cubes kind of only can be plus or minus 1. Not a mod 7. Obviously, if it's 7 cubed, then that's 0. So what I'm saying is that x cubed can only be congruent to 0, 1, or minus 1 under mod 7. And that is actually kind of a good property to use because obviously the first two are kind of well known, so they most likely will not appear in any of the big Olympiad exams, but this one might. And sometimes just choosing the right mod to look at a problem actually kind of solves half of it, which is really cool. Okay, so let's kind of do an example problem. So we do example. I want you to show that we have, if we consider this equation, so we have a cube plus 1 cube all the way to a plus 6 cube equals to b to the 4 plus b plus 1 to the 4. I want all of us to show that this equation does not have any solutions in A or B. So that's 6, that's not a B. So a cube plus a plus 1 cube plus a plus 2 cube plus all the way to a plus 6 cubed equals to b to the 4 plus b plus 1 to the 4. And we want to show that this thing does not have any integer solutions. Okay. I think I'm going to take 3 minutes before I just come back to this question. Okay. Okay, cool. So I'm just gonna come back to this problem and I'll kind of go over the solutions to it, right? So this basically actually directly uses the fact that um we have this fact here. So what we actually notice is that here we just have 7 consecutive cubes together, right? And we just found out that all cubes are 0, 1, or -1 under mod 7. So I think it is a reasonable kind of thing for us to do if we just consider mod 7 for both of these sides, right? So let's consider mod 7. In fact, actually, I'll write down all of the cubes um, under mod 7. So if we have 1 cube, 2 cube, 3 cube, 4, um 4 cube, 5 cube, 6 cube, and 7 cube. So obviously 7 cube is 0 mod 7. We have 1, 1, minus 1. This is just me copying from up here. And then we have 1, minus 1. And here we should have minus 1 mod 7, because 6 itself is minus 1 mod 7, and we can have minus 1 to the power 3 times, which is also minus 1 mod 7. Okay, and we know that this is 7 consecutive numbers, right? We have a plus 1, a plus 2, all the way to a plus 6. That is 7 consecutive numbers. So then we know that, well, okay. Then we know that the left-hand side is just some permutation of this thing, right? Whatever thing this is, whatever A is, the left side, because since we have a consecutive 7 numbers, the sum of the cubes must be a permutation of the sum of these numbers. Under mod 7, of course. So we actually just get that the left-hand side is actually congruent to 1 plus 1 minus 1 plus 1 minus 1 minus 1 plus 0, which is actually just 0 mod 7. So we have seen that the left-hand side is actually just congruent to 0 mod 7. Okay. Well, if this is 0 mod 7, then it will be very cool if on the right-hand side, it will always never be 0 mod 7, right? Because we are trying to find, or we're trying to prove that there are no solutions to A and B. We're trying to prove that there are no solutions to A, B, that satisfy this. So let's just look at the right-hand side in terms of mod 7. So if we have B4 plus B plus 1 to the 4, and let's analyze, well, the fourth powers on the mod 7, right? So if we have 1, 2, 3, 4, 5, 6, 5, 6, and 7, we see that, okay, 1 to the 4 is 1, and then 16 on the mod 7 is 2, and then 3 to the 4 is 81. Whoops, 3 to the 4 is 81, and then that will be, I believe, that'll be minus 3, which is 4 mod 7, and then we have 4 to the 4, which is 256. Okay, I think you get the point, but it's just you analyze each number to the 4 on the mod 7, right? And then you have 2 consecutive numbers, you have 2 consecutive fourth powers. So then you would just do this plus this. So that will give you 3 mod 4. Or you can do this plus this. That gives you 6 mod 4, etc. So you just keep doing this for all of these numbers, all the possible mod 7s that B can be. And then if you just do all of your casework, you will realize that, wait, this is actually just never divisible by 7. So on the left-hand side, it's always divisible by 7. On the right-hand side, it's never divisible by 7. So that's how we know that there are actually no solutions to A and B for this example. All right, cool. So that is kind of using mod arithmetic to look at these Diophantine equations. Okay, here is another technique, which is actually one of the cooler techniques that I know. It's called infinite descent. Okay, so infinite descent. Infinite descent is actually really cool because if you know about kind of the legend of IMO 1988, so 1988 problem 6, that's where kind of Vieta jumping came from. But the basic idea of Vieta jumping is actually just using an infinite descent. So what infinite descent actually is that if we can find kind of like a solution, I'll call it X, And then we can use that x to kind of get the next solution, right? So if we can find the next solution, x1, and then we can kind of do this repeatedly. We can kind of do this. We can just kind of keep doing this, right? So x goes to x1, and x1 might generate another solution, go to x2, that goes to x3. And then the argument is that we can do this forever. We can kind of generate infinitely many solutions. But then that can't becomes a problem, right? Because if we have some kind of condition that say x is bigger than x1, and then x1 is bigger than x2, x2 is bigger than x3, and stuff like that. And then you can generate infinitely many of them. Well, then the solutions must get infinitely small, right? Because you can keep doing this forever. But then if the problem statement goes like, okay, find all positive integer solutions um to this thing, then you realize what kind of cooked, right? That is because if you keep doing this, eventually you'll get to a negative number, and that's a really big contradiction. So that is the basic technique of infinite descent. I think it will make more sense if we do an example, right? Let's do that. Let's do another example, and then uh I'll just kind of go over the technique of infinite descent, and then you'll be able to understand what I mean, right? So this problem was actually on the APMO 2017 exam. So the 2017 exam of APMO, and this was the question 1 on that paper. Okay, so the problem goes, I have a circle, right? I have a circle of, and on it I have 2017 spots. So I've got all of these spots all around the circle, and there are 2017 of them. And on each of these spots is a integer. Okay, so we call this one A, B, C, D, E, F, E, F, G, H, whatever, right? So that goes all around the circle. There are 2017 of them. And the condition is that if we take any 5 consecutive integers, so for example, if I take this, so I have A, B, C, D, E, and I'll evaluate this expression. So I'll evaluate A minus B plus C minus D plus E, and that gives me 29. So basically, if I take any 5 consecutive numbers on the circle, and I do A minus B plus C minus D plus E, I get the value 29. So that'll be true even if I did B, C, D, E, F, and I do B minus C plus D minus E plus F. That will still give me 29. And the problem is just that find all possible ways that I can put numbers. I find all possible arrangements of numbers such that this is true. All right, okay. So that's the problem. But then my first thought to this problem was just that, wait, if it's asking me for all the possible arrangements, all the possible arrangements of the numbers around the circle, then surely if there are like 100 different arrangements, they're not gonna tell me to list all of them, all of them, right? That seems pretty ridiculous. So in my head, my thought was just that, okay, I'm going to look for the simpler arrangements of numbers. So obviously the first thing I thought about was, okay, what if all of them is 29? And that actually turns out to work, right? Because if you think about all of them being 29, then this and this cancel out, this and this cancel out, and you're left with this, and that is equal to 29. That is true for whatever, whichever consecutive 5 numbers you pick. In fact, it's true for whatever 5 numbers you pick, but yeah. And that turns out to be the only set of numbers that work. So that's the only set of numbers, and that's the only set of arrangements around the circle that makes this thing work. So the tricky part to this problem is actually just proving that this set of arrangements is the only solution. So we're going to be doing just that, right? So I'm going to do a bit of manipulation on it first. If I change this to A minus B plus C minus D plus E, and I'll move the 29 over, so that's equal to 0. I can actually go like this. So if I can do A minus 29, that's, what was that? B minus 29 plus C minus 29 minus D minus 29 and plus E minus 29 and the 0. This is actually true, right? Because I can just, if you look at it, the 29s kind of cancel out. I just did a manipulation, but this is actually pretty important. Why? Because I can then substitute whatever the number is at that spot. I can take away 29 from it, and the result is still true. Okay, so that's one of the things. I can just take away 29 from each of these. I can call it nodes, but I can just take away 29 from each of these spots on the circle, and the result will still be true. So I can actually make the substitution if I do M1 is this, M2 is this, M3 is this, etc. Yeah, and our task right now is actually to just prove that all of the m's must be 0, right? Because if we prove all of the m's must be 0, then we can come back and prove that all of the A, B, C, D, E's and stuff must be 29, and that is our desired solution set. Okay, so let's try that. So I'll redraw the circle. And we have M1, M2, M3, M4, M5, M6, M7, etc. You go all the way back, and this is M2017. All right, okay, so now we have the circle. I want to prove all of the m's of the thing. What we can do, right, is we know that M1 minus M2 plus M3 minus M4 plus M5 must equal to 0, and because that's just a condition. What we can actually do now is we can just go one spot more. So we can, instead of taking this section, we can take this section. So M2 to M6, right? So we have M2 minus M3 minus M3 plus M4 minus M5 plus M6 is equal to 0. And the reason why I did that is because there's a maximum number of overlaps between these two, and that makes it really easy to work with because I can cancel all of these, right? Then I'll get M1 plus M6 is equal to 0, right? Because M can be, the only restriction on M is that it's an integer, so that can actually happen. If M's were all positive integers, we'll be done already because sorry, if all M's are non-negative integers, we'll be done already because then that just means they're 0. But in this case, M can actually be negative integers, so we need to go further on than this. Okay, so we have M1 plus M6 is equal to 0. And what do we know about 0? 0 is a even number, right? Isn't, because it's not a conventional even number, but 0 is an even number. And what do we know about two integers that add up to an even number? What do we know about two integers that add up to an even number? Well, they are the same parity, right? They must be both odd or both even. And actually, in fact, only one of these cases will work. Okay. So if only one of these cases will work, that's what I'm gonna try to argue. All right. Cool. How I'm gonna do that? How am I gonna do that? So I know that M1 and M6 are the same parity. So if we just look at this big circle here, so that's just saying this one and then this one are the same parity. Oh wait, we can actually do better because we can actually do M2 and M7 are also the same parity by this logic, right? By the exact same logic. And we can kind of shift this kind of arc all around the circle because we can do M1, M6, M2, M7, M3, M8, all the way around the circle. And what is the gap we're going by? What is the gap? We're going by every 5, right? Because from M1 we jump to M6. From M6 we can jump to M11. So M6 and M11 is also the same parity. So we're jumping by 5 every time. And since there are 2017 of these nodes around the circle, and since GCD of 5 in 2017 is 1, we are actually just going around the circle 5 times before we go back at 1. If we just follow this train, right? If we just follow this train, M1 goes to M6, goes to M11, goes to M16. So that will go all the way to M2016. There are some thoughts. And then the next thing it goes to is actually, so it skips 2017, skips 1, 2, 3, and I actually go to M4. Right. Yeah, I'll actually go to M4, I think. Yes. Okay. And then it's like this, right? So M1 goes to M6, go to M11, go to M16, dot, 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 goes to M2016, goes to M4. And then we can start a new cycle. So what I'm saying is that if I go around the entire circle, all of the M's must have the same parity. So that is the big argument, okay? So all of the M's must have the same parity. Okay, and from there, you're pretty much done. There is one more observation you need to make. So I have all Mi are the same parity. Okay, so now if all of the Mi are the same parity, we can go back to our original condition, and that is Mi plus, sorry, nope, Mi minus Mi plus 1 plus Mi plus 2 minus Mi plus 3 plus Mi plus 4 equal to 0. Okay, so that is our condition, and we can pick I to be whatever index we want. And the additional condition is that all of these M's are the same parity. So if all of these M's are the same parity, we can actually deduce that all of them must be even. Why is that? Because if we think about all of them must be odd, we have Mi minus Mi plus 1, that's an even number, plus an odd minus an odd, that's another even number. So the first 4 evaluates an even number. This one's odd. And then we have odd equals to 0. And that's obviously just not true, right? So that's obviously just not true. So that just means all of our Mi must be even. And that is what actually gonna make this infinite descent work. Because why is that? Because if we think about Mi is equal to 2Ni, because it's even for some kind of n, right? If we think about it like that, then we can see that 2Ni minus 2Ni plus 1, 2Ni plus 2 minus 2Ni plus 3. And we can actually cancel out the 2's here. So we get that this is our new condition. Like this. This is actually our new condition. So now if we have this, we actually see that these two are the exact conditions. So we can do the absolute exact same reasoning on the ends as we did up here. So then we deduce that all of the ends must be even number, must be an even number as well. So that's where the trick of infinite descent comes from. So we can go from m's, so mi, and go to ni, and go to ni divided by 2. So all of these sequences actually are valid to our circle. Yeah, they all satisfy this condition. And here is where infinite descent comes in, because I can do this infinitely many times. But then that actually will force all of the m's to be 0. Because if we think about it, right, if m was not 0 at some point, or if some m was not 0, when we keep dividing it by 2, eventually we'll reach an odd number. And that is our contradiction. So I'll just write that out. Whenever we have mi not equal to mj, not equal to mj for some ij, we just have that when we divide m by 2 infinitely many times, so when we divide by m by 2 infinitely many times, we will end up at some kind of odd number at some point. And we end up at an odd number at some point. So that is our contradiction. So what can we conclude, right? What can we conclude? We can conclude that all of the mi must be identical. So then that makes it easy, because all of the m's are identical. Then we sub it into this, cancel, right? So this one kind of cancels, this one cancels, and we're just left with mi plus 4 is 0, and that in turn means all of the m's are 0. And so we have proven that the original must always be 29. Okay. So that is our APMO 2017. And we kind of just solved this with infinite descent, right? The idea of dividing by 2 each time. So I'm generating new solutions after each iteration. Okay, we have about 10 minutes. I think I have just about enough time to kind of squeeze in one more problem. I think I can do this in about 10 minutes. Okay, so last example. By the way, that's kind of like all the techniques I wanted to talk about for today, right? So we had an infinite descent. We can kind of analyze it with mod. And obviously at the very start, we can kind of factorize. So we wanted to factorize, modulus, and infinite descent. That's the 3 techniques we can kind of use to solve these Diophantine equations. So let's do an example problem. So we have m and our naturals. So m and our natural number. We want to show 3 to the m plus 3 to the n plus 1 is not a perfect square. Okay, So that is what we're going to do. So m and n can be any natural number. And if we substitute it into this expression, we want to show that it will never be a perfect square. Okay. So we're going to use one of our most powerful techniques, and that is proof by contradiction. Okay. So if we can assume that 3m plus 3 to the n 1 is equal to x squared. Right, it is equal to x squared for some x. And if we can find a contradiction, then we know that. Okay, if we find it's a contradiction, then we are done, right? Well, what do we know? Let's analyze both of these. Let's just look at the parities first. Okay, so on the left, this one is odd because we have 3 to the power something plus 3 to the power something plus 1. So that means this one must also be odd. So x is odd, first of all, right? So x is odd. What does that mean? Remember how I said all the way back at the top, x squared is only congruent to 0 or 1 under mod 4, right? X squared is only congruent to 0 or 1 mod 4. While here, if we look at it under mod 4, the right will always be 1, right? Because x is an odd number, and odd squared will always be 1 mod 4. So then that means 3 plus m plus 3 to the n plus 1 is always congruent to 1 under mod 4. Obviously, we can take away these. So we get 3 to the m plus 3 to the n congruent to 0 under mod 4. Okay. So it might be a good idea to analyze what the powers of 3 on mod 4 are now, right? Because we have the sum of 2 powers of 3s. So let's have a look. Because I'm sure there's going to be some kind of pattern, right? So if we look at the powers of 3, so you go from 1, 3, 9, 27, 81. The next one's like 2, 4, 3 or something. Okay, so if we look at it under mod 7, under mod 4, this is 1, minus 1, 1, minus 1, 1, minus 1, stuff like that. So that is quite interesting. The powers of 3s under mod 4, they kind of alternate between 1 and minus 1. Specifically, right? So we have to the power of 0, to the power of 1, 3 to the power of 2, 3 to the power of 3, 3 to the power of 4, stuff like that. So if we look at it, if we have 3 to the power of an even number, that will be congruent to 1 mod 4. And also 3 to the power of an odd number, that will be 3 mod 4, right? Because minus 1 is the same as 3 mod 4. And for the sum of 2 powers of 3 is actually equal to 0 mod 4, we must have one of them is odd, one of them is even. Because otherwise you literally can't have 2 powers of 3s that sum to a most mod 4. So then we know that mn is odd and even. Okay. So we know that one of them is odd, one of them is even. And that's just from mod 4. So we can actually try to analyze it under mod 8. Okay, so the squares under mod 8 are also quite interesting. Why is that? So the squares under mod 8, x squared is congruent to 0, 1, or 4 under mod 8. Yeah, cool. So x squared is congruent to 0, 1, or 4 under mod 8. And we know that x is always odd. So the only case that x squared can be is 1 mod 8. And that implies 3 to the m plus 3 to the n is actually congruent to 0 mod 8 as well. Okay, so 3 to the n plus 3 to the n is actually congruent uh to 0 mod 8. But here's where the contradiction comes in. Okay, we can do the same analysis of the powers of threes, but we look at them on the mod 8. And then we'll see something really interesting, because if we look at 1, 3, 2, 1, 3, 9, 27, 81, and then 2, 4, 3, what we actually get, this is mod 8, is that this is 1 mod 8, 3 mod 8, 1 mod 8, and this is 3 mod 8, 1 mod 8, 3 mod 8, etc. And it goes down like this. It will always go from 1 to 3. So 1, 3 mod 8. But here's where the contradiction comes in, right? Because we know that we have two powers of threes, and they sum to 0 mod 8. But the powers of threes on the mod 8 can only be 1 or 3. And that just gives us our contradiction, right? Because they can only sum to 4 mod 8, or they can sum to 6, or they can sum to 2, but they will never sum to 0 mod 8. And yeah, so that is our contradiction. So 3 to the n plus 3 to the n is congruent to 2, 4, or 6 mod 8, never 0. Oh, not 0 factorial, never 0. So that is our desired contradiction. And so we have proven that there are absolutely no solutions to m and n, with this being a square number. Cool. So that is our last example for today. Just to recap, right? Just to have another recap, we did our factorization up here. We did our modulus, and then we did our infinite descent with an APMO past problem. And then we also did another problem here where we kind of used the mod idea again, right? So we kind of used the mod idea again to show that there are absolutely no solutions to m and n. Yeah, that's going to be all from me for this session. Thank you, everybody. And then if you have any questions, yeah, you can always email me with any questions. Okay. Cool.